Wonderful. So in this piece of research, I'm going to be discussing analysis of feature engineering for dealing with URLs, and in particular, ideas about sort of the types of feature engineering that you might use that are sort of standard text-based NLP techniques versus custom ones, and how we can do interpretable machine learning on URLs. So the idea here is, is that? There we go. So a little bit of background, URLs are involved in most of our digital life. So, whenever we sort of retrieve news, we interact with social media platforms, use online applications, there's often URLs involved, but not just human to machine interaction, also machine to machine interaction. So increasingly, a lot of computer systems that use APIs actually use URLs to interact with each other. So, which means that URLs are useful both for machine learning applications that are about human to machine, but also machine to machine communication. And they're critical to a lot of online machine learning applications for different kind of users. And for some of these applications, because they have latency considerations, i.e. the machine learning system needs to react really quickly, often the URL is the most important piece of information it has available to it. So it means that it's a really critical thing that we focus on in developing these machine learning systems. So, yeah. So, I thought there was another slide in there. So now, in standard applications of machine learning that use URLs, it's quite normal to treat it as just as a blob of text and apply standard techniques to it. But actually, URLs are quite structurally unique in that the different components of the URL have different pieces of meaning, and you can actually apply a lot of bespoke feature engineering to them. So this illustration sort of shows you some of that structure. At the start, you have the protocol, which indicates the type of content that's being retrieved. So here you've got HTTPS for secure hypertext transfer protocol, but you can have FTPS, and there's also not only are there open standards like HTTP and FTP, there's also a bunch of proprietary standards that are used by things like, say, I believe Spotify has their own protocol, etc. So a lot of data communication platforms have their own protocols. Then you have the host, which is actually broken up into the subdomain, that www at the start, the domain name itself, which is really just a sort of a standard piece of text, and then the top level domain, the .com here, which is in some sense indicates the purpose of the domain, but also can indicate geographic region, because there are sort of there are top level domains for particular countries, but also for things like a .edu or a .gov, indicating different types of organizations. Then you have the path, which is historically that was just a series of Unix directories, so it indicated the location on the file server. But increasingly, as applications generate internet content, these are actual virtual paths that indicate something about the internal structure of the application. You have the file name itself, which is the name of the file is kind of informative as a piece of text, but also the file format can tell you things like, is it static or dynamic content, the type of technologies that are being used, etc. And then everything following the question mark is the sort of URL parameters that indicate, again, whether it's dynamic content, how personalized it is. So there's a lot of information about the content of the URL from sort of after that question mark. Now, so each of these different components of the URL you can treat using very, very custom feature engineering. So that protocol itself, it tells you the type of content that's being transmitted. So HTTP means sort of text and internet pages. FTP means a file transfer. But the addition of the S at the end gives you additional information, like the fact that it's encrypted. So you can come up with very, very bespoke encoding schemes that indicate not only the type of application, but the kinds of constraints like encryption that have been added to it. The domain, the host can be broken up into that subdomain, domain, and top level domain, and each of those things you can do encodings for. So, the subdomain, the thing like the www can be, you'll also see common ones will be mail or admin. indicating that the page you're accessing might be an administrator's page, or it might be an online email application. So the subdomain is often indicative of the kind of content, and the subdomain gets used in very, very tricky ways by pranksters and spam artists when they're trying to sort of fool you. I'll talk more about that in a moment. And then the top level domain, as I mentioned before, can indicate geographic region as well as sort of business applications. The path itself is in some senses a pretty good sort of just pure text play. It's often a sequence of words separated by forward slashes, but you can also analyze it for the depth in the directory, can often be an indicator of the specificity of the content. Or versus, is it sort of a general page? The file, there can be naming conventions in the file that are useful. So for example, some content management systems or blogging software will actually put dates into a file name or add unique identifiers, but often they'll remove stop words and just keep the sort of the key sort of nouns, verbs, and adjectives in the name. So there's NLP data in the file name itself. And then the parameters are a rich set of key value pairs that can indicate things like what people were searching for, unique identifier strings, meant all kinds of different information. So it should be clear that it's not like English or any other language text. There's very, very specific bits of feature engineering you can do with each part of this domain. So one of the main things that we're interested in this research is, there seems to be a lot of slides missing. I think I've sent you an old version of this presentation. All right, I have to talk to the things that's not here. So there's a few slides missing. The first thing is that historically, when people process URLs, they tend to do one of two things. They either just treat it as a blob of text, where they use standard NLP techniques, like you do bag of words, TF-IDF, some kind of n-gram, or maybe some custom regular expressions, or they use a neural network technique to try and learn some kind of embedding. So you treat it as raw text again, and maybe use a recurrent network or a convolutional neural network or a skipgram kind of model, some kind of model that breaks it up into text first. Then you find there's a bunch of niche papers where they focus on building something very, very specific for a certain kind of problem. So for example, it could be for like in a lot of the internet security problems, which you'll be interested in, they do very, very specific feature engineering, but a lot of that information gets lost in different papers. And so the motivation for this work was we wanted to build a reusable library where we could bring in as many different feature engineering techniques for these different parts of the domain. So you can just pull them into your problem, apply them and test them. But we also want to imply a naming ontology on top of them that tells you which part of the domain, which part of the URL, sorry, it comes from, so that you can then do interpretable machine learning on top of it. So the last part of this talk, I'll be focusing on techniques for visualizing where the information in a domain comes from for a particular kind of problem. So that's the motivation. Reusable library that we can release so that we can bring in new features that you can use easily, and then allow you to do interpretable machine learning doing that library. So we have an implementation as a Python package. You can pip install it and use it as it's shown at the bottom here. So it's a command line application. In this application at the bottom, what I'm saying is after I've installed it, you have to tell it the column of text in the data set that contains the URL. In this instance, you use command line switches to say the kinds of features you want. So I'm saying just extract features from the host, that's the subdomain, domain, and the top level domain, and then also I give it the input CSV, and then it outputs it to another CSV. Yeah, so it basically easy to apply. You don't have to take all of the features. You use the switches to say which features you actually want for your problem, and this command line application can deal with arbitrarily large data sets by using internal chunking. So it will test, is this data set too big for me to handle in memory, in which case I break it up and I just process it piece by piece by piece and then output the whole data set. So hopefully it will facilitate more greater experimentation in URL-based machine learning. So maybe you'll find it useful. So not only can you use it as a command line application, it's also scikit-learn compatible. So for those of you who are not familiar, scikit-learn is the kind of the go-to Python package for machine learning. A lot of other packages make themselves compatible with scikit-learn. So it has this notion of a pipeline. So you can construct a series of data processing steps that ends in a machine learning application in one of these pipelines. And it's actually relatively simple when you build a library like ours to make it scikit-learn compatible. So basically what that means is you can import our package and then include these URL transformations in your pipeline. So what I've done here is the same thing I showed on the previous slide, where basically I'm give me host and top level domain features. I tell it that its URL col contains the URL. It'll process those features and then it'll feed it into that classifier algorithm at the bottom there. So easy to use in multiple pathways for making use of it. Cool. So that's the first part, the sort of the motivation for building the library and how you use it. Then we wanted to do a set of experiments to get a sense of both how useful is the library and also how can we use it for interpretable machine learning and understand where information comes from inside domains. So in this case, what we did is we took a set of open data sets that contain URLs as the main kind of feature. And what we're going to do is we're going to try and complete the classification task using only the URL, ignore any other information that's available. And we're going to test multiple out-of-the-box machine learning algorithms. We're not going to do any hyperparameter testing because we're not trying to find the perfect model for these problems. We just want to get a sense of what works using URLs. We're going to choose the best model, and then we're going to do some experiments to try and understand where the information comes from these problems. So we're going to use something called Shapley values, which is a highly recommended package for doing interpretable machine learning. What it basically tells you is, of all of the features that are available in your data set, which ones contain the most information for the task you're doing. And there's multiple ways of visualizing that. And then we're going to group the feature importance by the kind of ontological segment of the URL they come from so that we can visualize that to understand where the information comes from. So the data sets we've got here, there's 6 of them. The first 3 are internet security data sets. So there's a spam, malware, and phishing. So if you're not, spam is effectively when people are sending you unsolicited emails, potentially for malicious purposes, sometimes for just sort of dubious marketing campaigns. There are many, many different types of spam. There's also very specific types of malicious activity. So malware is trying to get something installed on your computer that's going to do something that you don't want it to do. And often they can be communicating with back-end services trying to steal your information. So there's URLs in that back-end communication. And then phishing is when someone is trying to get you to click on a link in order to collect your data. Like they're trying to convince you that you need to log into your bank, change your account number, but actually the URL is not your bank, it's someone else. So detecting those phishing URLs is a really important problem. The final 3 data sets are all about classification of URLs. So the WebKB for Uni is an old data set of different URLs of different universities where you categorize it into things like course content, research pages, personal pages. And SciSkill and Webbit is a really unusual data set. It's very small, but what it contains is one individual's personal preferences about a whole lot of different websites, the websites they like and they don't. And then the DMOZ data set is a Kaggle data set of categorization of content into categories related to the things I was talking about in the earlier presentation, where you want to know, is this a sports website? Is it an automobile website? Is it a pet's website, etc.? So 4 different data sites. They're all classification, but as you can see, the number of classes varies. So the first 3 being binary, the others being multi-class. They're all imbalanced data sets, as you can see in them. So the majority column there tells you what's the percentage of records that the majority class contains. And in all instances here, these are all imbalanced data sets, although the size of the imbalance varies. So because of that imbalance, I'm just going to talk about balanced accuracy. It's just the arithmetic mean of recall and specificity. It's just a simple way of understanding accuracy performance when you've got imbalanced data sets. And so in this test, we just ran 4 algorithms. Naive Bayes is NB, LR is logistic regression, XT is the extra trees, which is a random forest implementation that's available inside scikit-learn. And then we installed the Light GBM package, which is a really highly performant gradient boosting implementation from Microsoft. So I'm reporting the balanced accuracy here. First thing that should be apparent is, interestingly, in all of the internet security problems, you can do really well just from making predictions on the URL. It's probably unsurprising because most of the vulnerability is through the URL. Like these are basically criminals trying to deceive you with URLs. So most of the information is there. In all of the classification tasks, it's much harder. It's much harder to perform well purely based on the URL, but it's probably more better than you might think, given that you're trying to the URL is here standing for the whole content of the web page. It indicates that there is quite a bit of an indication of what's going to be on that page, just encoded into the URL itself. So for the feature importance, what we do is we have a holdout data set in each case. We've kept that to 80 to 100 data points, depending on the data set here. And then what we do is after we've scored the holdout data set with the models, we use the Shapley package. So the Shapley package will go through each of your predictions on the holdout data set and tell you which features were used to make most important to make those predictions. And then what you can do is then take the average importance over all of the samples in your holdout set, and you get a sense of what's the average importance of those features to this particular problem. And so then what we do is we can then group those by the part of the URL they come from, and then visualize that to get a sense of and allocated to each of the URL segments. So that's what we've done here in this illustration. This isn't part of the package yet, but it's the script for doing this is available inside the open source library. And so at the top there, you see what I've got is a kind of canonical representation of the structure of the domain, of the URL, sorry, as before. So protocol at the start, subdomain, domain, top level domain, etc. And then what I've done in the gray, I'm showing the gray sort of bar through the middle is features that were generated from the whole URL. So we have a few things there, like what's the length of the URL in characters, what's the proportion of the characters that are numeric, what's the proportion that are not alphanumeric. So just general standard features that involve the whole URL. And then the rest of them, those sort of green boxes, show you features derived just from that specific part of the URL, and the intensity of the green shows you how important it was. So interestingly here, what you see is that, so for example, in the 3 internet security problems, spam, phishing, and malware, the overall URL length and those kind of features weren't very important at all. And most of the information is coming from the domain part, like it's the subdomain, domain, or top level domain for that spam one. And this actually sits well with what you'll read in the literature about particularly phishing, because quite often what criminals who are trying to phish you for your information, they'll put the name of your bank as the subdomain. So they've registered some random domain like xyz3241.com, but then they'll put commonwealthbank.xyz. So they put the name of a legitimate business in the subdomain because they're able to do that. And so at first glance, people think it's a real domain, click on it, and so that's how a lot of phishing URLs work. So it's unsurprising that this method is kind of picking up that as being the predominant source of information for phishing domains. Whereas other applications, notice in, say, the DMOZ or the WebKB, you've got a lot stronger emphasis on the path and the file name itself, because these are categorization problems. So actually, URLs often contain structural hierarchical information like news, sports, rugby is a kind of, it contains a categorical structure that indicates the kind of content that's contained there. So it kind of indicates what you can, it indicates that's where most of the information is coming from for these particular problems. So again, nothing groundbreaking here, confirming what we kind of know about these problems. But what it does tell us is this way of visualizing information in URLs could be useful for new problems where we don't already have this knowledge of where the data comes from. You can use a library like this, generate a bunch of features, visualize the source of the information, and then that can direct new feature engineering and say, okay, I'm getting information from the path. Let's build some more custom features for the path or apply different techniques there. So hopefully that the sort of summary here is URLs are really rich in information. They are text data, but they're also not text data. They contain information beyond the text. Some of the information can be extracted with standard techniques. Some of them often require use of supplementary information, reference data, sort of domain name registrars, that kind of thing. There are latency considerations because a lot of these machine learning applications that use URLs need to respond quickly. So you do need to, unlike the standard way that you go about doing feature selection, which is all about focusing on performance, sometimes the engineering here needs to be, how much information does this feature give me versus how long does it take to compute? Do I need a lookup table, and how quickly does my system need to respond? So this kind of exploration can allow you to do the trade-offs between performance and latency. And that analysis suggests really strongly that you can see really big differences in where information comes from in URLs for different applications of machine learning. Oops. Yeah, it's completely missing. I don't know which version of this, but there's a whole slide missing. Anyway, thank you for your time. Any questions?